Okay, yes, now I am recording it. Thank you for reminding me.
All right, thank you.
Okay, so what am I trying to do here? Trying to multiply 0.34 by 2100. So 714. So we're going to have 0 plus 714 divided by whatever, 2100. Should be a square there. It's a rather large number. You can just leave it like that for now, so I'm not writing as much. So that gives us a scalar. We're going to multiply by this. And I'm not going to keep showing all the work in between, but if we finish that multiplication off, what we should get is I wrote the wrong vector in here. This isn't the one we wanted, I'm sorry. Yeah, that one shouldn't be there. We want the direction vector. That should have been vector B. So I'm sorry, I wrote the wrong thing there. That should have been 0.94, negative 0.34.
So would that make the bottom?
Yep, messed up there too.
I was
Okay.
going to ask that when we were all
Yeah.
done.
I'm sorry. Okay, I was wondering why I was getting such a large number down there, because that's not what's supposed to be there. Apologize. My bad. All right, so what we should have gotten the denominator then, 0.94. Oh, where'd my calculator go? Plus 3/4 times itself. All right, 0.9992 is what we should have gotten down here. There we go. That makes more sense to me. Okay, so now what we get for a final answer for this, if we go through and multiply it all out, I mean, you can try with a calculator, but 674.7 for the first component, and then for the second component, 245.6. Yes, right.
My question is on the sine cosine. Why does that equal vector E and not vector U? Because when we were doing it here, it was vector 2.
Okay, so don't think so much about the picture, think about what direction we're trying to go. And so the goal of what we're trying to get here is say, okay, we need to go up the ramp, right? I mean, we're not quite done just yet, but the ramp is really the direction that we're talking about the movement in. So vector V in the formula we had for the definition of projection, V is always talking about the direction that we're traveling here. So that ramp is our direction vector. So even though the picture we have kind of makes it look like we should flip letters around, the direction we're trying to travel in is what V is, so that's why the ramp is V.
Okay.
Does that address your question?
Yeah, so what's the difference of doing it, but like back here we multiply by the magnitude line, not or the cosine of theta times the magnitude of E.
Back where?
On page 7, like the formula.
We don't have the magnitude of V right now. If we knew how long the ramp was, we can multiply by it, but we don't have that information. The only thing we need to know about the ramp is what direction it's traveling in. So if we have a small ramp or a long ramp, it's still going to be the same direction. So we just didn't have that in this one here.
Oh, okay.
So yeah, we just didn't know what the magnitude was, but it worked out okay because we just need to know the direction it's traveling.
That makes sense.
Okay. All right, so we're not quite done, but we're close to done. What do we have right now? What does this vector tell us? What does this mean?
Just going the wrong direction.
Yeah, right now we're going the wrong direction here. So if we think about this vector is telling us that the force that's happening right now, or that component, is still traveling down the ramp there. Okay. Although it's not, one of these should be negative. This should be a negative. If I could multiply correctly, we'd see that there. Sorry, positive number times a negative 0.34 should have been a negative. So yes, it is going the wrong direction. You were right. The picture you had was right. So right now we're going the wrong direction down the ramp there. We need to flip this thing around. Okay, so we want to know, like we said, even though we can go through and find this blue vector we sketched up here, what we really want to know is this pink one, what's going the other way. So just multiply both by -1. So the force vector we actually are interested in is going to be negative 674.7 and positive 245.6. And to know actually how much force the truck would have to be applying, we haven't talked about this directly, but that's what the magnitude of this force vector represents. It says, okay, well, how much force actually is the truck going to need to do here? What's the actual foot-pounds or inch-pounds or I guess just pounds in this case, that we're going to be working with. And so if we find the magnitude of this vector, that's going to mean more to what the truck is actually doing here. Because you can tell the truck to go off in this vector direction, but it's probably not going to make much of a difference. If you know how much force the truck has to be applying, that's a bit more meaningful here. So if we find the magnitude of that, that's actually the force that would need to be applied to keep the boat from rolling down the ramp here.
So this is the force that the ramp is exerting on the boat. That's going to multiply by -1.
So again, this is the force of the ramp.
The force of the ramp is pushing on the boat.
Basically, yeah. So this right here, this is how much the boat wants to move down the ramp. So it's the force the boat wants to move down the ramp with. But we want the opposite of that. We want to just keep the boat still. So that's why we're doing the opposite of that. We're going to just reverse its direction, but not change the magnitude.
Okay.
If we change the magnitude, now the boat's going to start moving up the ramp.
Yeah.
If we don't change direction, we're basically pushing it down into the water.
Okay.
So yeah, we just want to cancel this thing out. So take the opposite of it. If we go through and find the magnitude of this, I think if I have my notes written correctly, we should get 718.2 pounds. Okay, and that's how much force the truck would actually have to exert on the boat to keep it still on the ramp, to not let it slide into the water, to not pull it back out. That's how much it would have to do there. Okay.
So we start off away. So so the length is pounds on this instead of length.
No. So this
So
now we found the magnitude.
on the magnitude.
Yeah, so the magnitude here is now in pounds. Because like think about if you're finding like
Something like usually think of magnitude.
Right. So if you think about like a vector that's talking about how fast we're going. So like we're going somewhere. We start here, we go off to someplace there. The vector tells us basically the directions the way we're going to get there.
Right.
Okay. If we find the magnitude of that vector, we know basically how far we've gone there. And that would then relate to speed. So if we know we travel this vector in like a minute or a second, we can translate that back to speed there. And so that's kind of happening here. What this tells us is this is what you have to do to actually keep the boat still. But in this case, it's not really a matter of distance that we're keeping the boat still with, because we're not really traveling anywhere. We're just applying force in the beginning. And so that's why we're going back to that applying force in the beginning.
Right.
Because we weren't really moving the boat in the beginning. We just were applying some kind of force to the boat in the beginning. Okay, other questions?
I'm logging off, just saying.
Okay, all right, and I will upload this and try to remember to send you notes later, okay?
All right, thank you.
All right, bye, Stephanie.
Bye-bye.
All right, so that's dot product. Most of the time we're using dot product, it'll just be mathematically just finding dot product, or in terms of components and vectors and projections, okay? We really don't do as many word problems as maybe this would seem like it is. A lot of the stuff we're gonna work with is more similar. We had example 5 where it says just define the projection. What is the projection there? This stuff in Calc 3 has a lot more application. We have higher level stuff here. So even though I'll try to put in word problems at this point, this isn't really the focus of what we're doing right now. Word problems will show up later. All right, so let's move on to the cross product, the other way we can multiply vectors. I didn't put a link in here for it, but the guy from Better Explained does a good job of going through and talking about cross products as well. So if you want to go through, even has a link at the end of the other one, you can go through and do this. But this is a different way to go through and multiply vectors here. So jump down to this little grid, and I'll try to explain kind of what we're doing here. We are only going to work with cross products in 3 dimensions. Make sure cross products. Okay, we're not going to work with cross products in 2D or 4D, just talk about 3-dimensional cross products. Okay, so let's say we've got 2 vectors, and we'll keep with our traditional vector u. We'll say the components are u1, u2, and u3. And let's say vector v, same thing, v1, v2, and v3. Okay, how many of you have heard like the box method for multiplying polynomials?
Lattice.
Huh? Or lattice method, right, for multiplying, yes, same thing there. And that's really what we're going to go through and do here. So if we've got our 2 vectors, we're going to go ahead and write their components. One across the top, one across the front row column, I guess it is. And then like when you multiply, you just multiply all these parts together here. So I'm going to write 2 things in this box. So I'm going to write my little u1, v1 small up top here. But we can go through and we can multiply all. These are just a bunch of numbers. u1's a number, v1's a number. We can multiply all this stuff together here. Okay. So we've got 9 different little parts that we're talking about. So when I'm thinking of multiplying a vector, these are all the possible different ways I could multiply the parts together there, right? Nothing's really left out. Everything's been accounted for here. If we think about going down that first diagonal that starts here at U1, B1, and kind of travels throughout there, what these guys represent, or these guys show, these guys, I shouldn't use crosses, that looks deceiving. I just meant to mark them somehow. Okay, what these 3 guys represent is pretty much what the dot product does. When we found the dot product, we took U1 times V1 plus U2 times V2 plus U3 times V3, and we added all those things together. So if we're thinking about all the possible combinations of the parts of the vectors we can be working with, we've already counted for these 3 parts of dot product. We kind of addressed those. So what the cross product is going to do is going to be a way to deal with all the other parts that we have left over there. And so we're going to find a way to deal with that U2, V1, U3, V1, and all those other little pieces there. So if we think about, and the guy in the book talks about interactions in the same direction or different directions or something like that, the dot product's job is to say, okay, all the like parts, so things in the same direction, V1 and V1 both in the X direction, U2 and V2 both in the Y and both in the Z, already taken care of. What the cross product does is it looks at the interactions that are moving in different directions there. So we're going to say, okay, U2 is talking about a change in the Y direction, but V1 is talking about a change in the X direction, because that first component, that second component there. So if we're trying to match up different components, we need a different way of dealing with that. And that's what the cross product's job is to try to do here. We'll come back to what it means, but mathematically how you find it is this big nasty thing here. Okay. To find the cross product of 2 vectors in space, so again in 3D, when we say in space, we're talking 3 dimensions, not just on a flat plane there, is we're going to go through and do all this stuff here. Okay. We use just the X to represent cross product, much like the dot product is a dot. This is not something for me that I can remember here. So luckily there's another way we kind of look at where this comes from. If you've worked at matrices, you may have worked with determinants. I know for at least this school, we don't require any matrices before you get to Calc 3. So real quick, I think we all remember what a matrix is. So if we have a 2x2 matrix, okay, a 2x2 matrix means you've got 2 rows, 2 columns. Let's just say A, B, and C, D for now. Okay. Do you remember maybe using matrices to solve systems equations? Maybe.
Once.
Yeah, it's not something we really do a whole lot
We
there.
didn't really do it in my school.
All right. Well,
Very rarely.
at some point, you may be lucky enough to take a matrix theory class. Matrices are wonderful. What they do is they take things that are repetitive and they basically remove all the repetitive part and just focus on the content, on the numbers. So it simplifies a lot of higher level math there. Anyway, there's this thing called a determinant. So what a determinant is, and we just abbreviate it DET. So if we're going to find the determinant of this matrix, what that is defined as is kind of like cross multiplying. We're going to take A times D, and we're going to subtract B times C. And that is just what's called the determinant of the matrix. Right now, this does connect back to the cross product, and not just crazy and talking about things that don't matter here. So in our case, the way this could be useful is if this isn't something you're going to remember, like for me, this doesn't make, my brain can't connect those things together. So if I can read it, I can write it down, sure. But if I'm trying to be able to do this quickly, I don't want to go back to the formula here. Here's basically what's happening there. So for our case, another way we can think about where the cross product comes from is we are not working with a 2x2 matrix. I mean, we just said we're working with 3 dimensions here. So we're going to make a 3x3 matrix, which means we have 3 rows and 3 columns. Across the very top row, we're going to put those standard unit vectors, I, J, and K. Okay, again, what do these guys mean? What does vector I represent? And then J represents Y, and K represents Z. Okay, so 1 unit change in each of those directions. We know what those are. What we're then going to do next, we'll stick with the same notation that we have up here. If we're doing U cross with V, we're going to put vector U in the next row. So we're going to take its components, U1, U2, and U3, we're going to put them there. And then same thing with V, V1, V2, V3. We're going to stick its components down here. So there's our 3x3 matrix. Okay. To find the determinant of this, we have to kind of go back to this 2x2 matrix idea, but this is really just going to show kind of where these combinations come from. So let's say we're going to do this. If we want to find the kind of first piece of this, we're going to figure out where this little section right here comes from in that I direction. We're going to say, okay, basically take this I And if you don't want to cross yours out, that's fine. So I'm going to erase this in just a minute. But imagine crossing out all of this stuff and just focusing on this little matrix right here, this little 2 by 2 matrix. Okay. If we've got this little 2 by 2 matrix, U2, U3, V2, V3, find the determinant of it like we just set up here. We're going to take the cross product of U2 times V3 minus U3 times V2, which is exactly what this says right here. Okay, so that's where this comes from. It's basically saying, okay, we've got this 3 by 3 matrix we're kind of building, and we want to know in the I direction, we're going to ignore that row and that column and focus on what's left over and find the determinant of that. To then go through and find it in the J direction. And again, like I said, I can erase all this stuff easily here. When we go through and find it in the J direction, we're going to ignore all this. We're going to ignore this. And we've got this little 2 by 2 matrix built from these guys over here. The same thing happens. U1 times V3 minus V1 times U3. That makes up the middle component. Okay? And then the same thing for the last one. If we cancel out what happens for the K direction. Okay. If we cancel out and do what happens in the K direction, same thing, ignore this, and if you focus on that, that's where the little component comes from. So again, that determinant is kind of a, I don't know if I want to call it a shortcut, but it's kind of like where that original formula for cross product comes from. You're building these 3 little determinants and going through and finding the determinant of those. Now, your fancy calculators will do this stuff for us, but I still want you to be able to do this stuff by hand. Okay, I'm kind of old-fashioned in that regard, and I want you guys to be able to understand what's going on enough to be able to do it yourself. So here we go. Next page, we're going to do one with numbers, actually. All right. So we got this vector U, we got this vector V, and we want to find the cross product of U cross V. Okay. Notice in B it says V cross U. All right. So we'll see what happens here when we do those two things. But let's just start off with this. If you're comfortable using that just long equation formula that gives you that standard combination form, go for it. I like to set up that little matrix and determinant there. So that's what I'm going to go through and do. So off to the side here, I'm just going to draw that IJK matrix. U comes first, so component form for U, the components of that are going to be 1, -2, and 1. And then for V, I have 3, 1, -2. And this just, like I said, for me, it just helps me organize what I'm doing a little better here. All right, so here we go. We are going to ignore this information here and just focus on this little box right here for now. Okay. So the determinant of that, we're going to have -2 times -2 minus 1 times 1. And all that is going to be in the I direction. Okay. So we take that little 2 by 2 matrix and we take across the product from going one way, the product from the other way, and we subtract the 2 of those. For the next one, we're going to then focus on this outer row here and this one here, so we're ignoring what's in the middle. Then we can go through the same thing. So note that we are subtracting what happens here. So we're going to have 1 times -2 minus 3 times 1. And that is what's happening in the J direction. And then we got, oops, too much there. And then one more, we'll go in the K direction and do the same type of thing. Okay, one more color. All right, so in the K direction, we're going to ignore this and just use this little box right here. And then we go back to adding. And so what are we going to get? 1 times 1 minus -2 times 3.
So it's always minus and then plus?
Yes. Yep. So positive, negative, positive, the terms go. First thing is just positive. That middle piece is always going to be subtracted, and you're always adding the last one. Okay. And like I said, if you're fine with just remembering or just going back to that formula, go for it. But like I said, for me, this just, I make less mistakes when I do it this way by hand. So I like to do it this way. But I'm not going to require you guys to do it the same way I do. But I will like you to get the right answers. All right. So what do we get? We get positive 4 minus 1 in the I direction. So that's a mix of 3. And then over here, we're going to have -2 minus 3 times J. And for the last one, that'll be 1 minus -6, so plus 6 times K. So 3I, -5, so plus 5J, and plus 7K. Right? See if we have before. If you want to leave it here, that's fine. If you like component form better, go for it. Both answers are okay. A bit more involved in the dot product. Remember, we're incorporating a lot more pieces. A dot product is looking at 3 parts of all the possible things we can be multiplying. This is looking at a lot more than that. It's a bit more complicated. Also note, is the answer to the cross product a vector or a scalar? A vector. We're using a vector out of this. So dot product just gives us a scalar for those 3 terms. Cross product gives us a vector for all the other pieces there. Okay. And this vector does have a nice property we'll talk about in a minute. It wasn't in the notes, but I skipped it. It comes up in just a minute.
So if you ask why the vector or is that probably that?
You can ask why, and I will tell you I can't give you a good answer for that. I don't know. That's why that better explained. If you go back to that, he probably is a lot more graceful trying to explain it. Yeah, I don't have a good way to explain that. It just is. Which isn't a good answer on that. All right, try the next one on your own, okay? Whether you do it the same way or do it using the formula. So same 2 vectors, you just flip in the order. Instead of u cross v, you're going to do v cross u. So take a little bit, set that up, work through that one, and see what happens. And if you get that one finished, feel free to do part C also.
When you start seeing now, you see that. Yeah.
I can't see which problem you guys are on. Stuart, how are you guys doing? You get part B done? Are you working on C or are you still on B?
Oh, I wrote too much. Yeah, I thought I wrote A to B, so I thought it was better for C.
Oh, you've already that down with B.
Yeah.
All right, let's go ahead and I'm not going to go through all those. If your answer is wrong, we need to check it. We can. But volunteer, what do we get for B when you work through it?
-3 and -5 and 7.
Mm-hmm. Okay, and if like the component, the other form better go for it there. Similar, same, different. What's going on between that and A?
Opposite.
Yeah, it's opposite. Okay, which means if we think about multiplying, cross multiplying, is that commutative? Can we switch the order around?
No.
No, it makes a difference here. Okay, so most of the time multiplication is commutative when we're talking about just numbers, whatever, flip the order, you're fine. We're talking about dot product, whatever, flip the order, you're fine. But with cross product is different. Okay, order makes a difference here. We're ending up with a vector. In part A, our vector was going off in the positive direction everywhere, and B is just going the opposite direction from there, okay? So they're still parallel vectors, but they just have different directions. So order definitely matters. Order matters for cross product. And that's not something we had before. I know at least one of you guys got through part C. Anyone finish at C and want to share the answer?
Zeros.
Yep, a bunch of zeros. Okay. So when you cross a vector with itself, you just get a bunch of zeros out. And you can go through the math and you'll see pretty quickly that everything just starts to cancel out there. Okay. Most of the stuff is summarized right below there with some of the formulas here. But just to go through and kind of show it. There is one more thing that we'll go back and take a look at these examples in just a moment here. So there are some properties of working across products. Put algebraic and geometric for those properties. Here's that one where we just said is not commutative. The order matters. If you flip the order, you get the opposite direction. It makes a difference. If you're going to cross it with a bunch of zeros, so if you imagine one of these vectors was just composed of zeros down here instead of numbers, obviously everything's going to go to zero. It's just multiplying and adding and subtracting a whole bunch of zeros together. So that shouldn't be too surprising, that second one there. For that third one, it's a way of going through and distributing. We can see if we can still distribute with the cross product. This one we saw in part C, a vector cross with itself gives a 0, which is a little weird to kind of think about, but hopefully we'll fix that in a minute. Scalars you can go ahead and distribute by, that's fine. Just make sure you only multiply one of them by the scalar, not both of them. And this number 6 here, this is called the triple scalar product. We'll talk about this more a little bit in the notes too. Okay, it's combining dot products and cross products into one, which is kind of weird. Think about the answer you're going to get from most of these. So for 1, this is giving you a vector. This is giving you a vector. This is giving you a vector. 0 vector, but still a vector. Are we getting a vector in number 6?
No.
That's going to give us, yeah, anywhere to dot products, we're going to get a scalar out of this one here. So like I said, we'll talk more about that triple scalar product later. Just list them all in one spot. There we go. Now here's where this becomes more useful. This is listed previously in the notes, but I skipped over it because it didn't really matter then. It's important. When we take the cross product of two vectors, the resulting vector we get is orthogonal to both of the other ones. Okay, and what does orthogonal mean? Perpendicular. Okay, so we get this new vector that's perpendicular to the other two vectors here.
So what you're saying is U and V have to be parallel.
Not parallel. So what U and V are is in the same plane. Again, I guess I have big sticks here, right? So if we've got some vector U going off in some direction, three-dimensional space, and some other vector V going off in another direction here, no matter what, these guys form a plane, right? If I had like a really heavy or a really strong arm here, I could hold a piece of that I could put a piece of plywood on top of here and it would rest. If my vectors go this way, it's still a plane. If I go this way, it's still a plane. No matter where these vectors go, they make a plane, right? So what we're saying is if these are our two vectors we're starting off with, I have a third ruler, but the cross product is perpendicular to both of these.
They're plane.
So they're plane. So to just one of them, it's perpendicular. To just the other one, it's still perpendicular. To its plane, it's perpendicular, but that's what the cross product is doing. No matter where these vectors are in space, that orthogonal vectors the cross product tells us.
I got you.
Okay. Sorry for throwing words. Yeah, just coming off in some other direction there. Okay. That turns out to be super helpful. It's nice to be able to find something orthogonal, third dimension there. So cross product gets used a lot for that regard there. The second one we won't really see a whole lot, but there you go. The magnitude of the cross product equals that thing there. Two vectors are going to cross and equal 0 only if they're scalar multiples of each other. So if we think about that in this too, if U and V are scalar multiples of each other, it means they're parallel, right? So maybe one's shorter than the other one. Maybe they just go off in different directions, but they just form a line. Do we know what plane this line is in? Does this make a plane just having a line? No, I have to have some kind of angle to it, right, in order to be able to line. I mean, if I have these were round actual lines here. I mean, I don't know where to put that piece of plywood. I mean, is it going to go vertically? Is it going to go horizontally? At some angle there. So what this is basically saying is if we have two parallel vectors, we really don't know what plane they're in, and so we can't find a perpendicular vector to this. So that's how we get 0. Okay? And then the last one turns out to be somewhat handy. It's kind of interesting there. The magnitude of the cross product is the area of a parallelogram. So I'm not going to try to prove that, but it's just kind of an interesting thing that's here. So let's do, actually, instead of the example, we'll do that next time. Let's go back up to these guys over here, and let's verify that orthogonal piece. Okay. So we said that the cross product is going to be orthogonal to both U and to V. So let's use the work that we already did over here. I will just do it off to the side right here.
So let's say, does that include V and V?
No, because like we just said, V and V would be parallel vectors, so we don't know what plane they're in. So when we find them, we just get 0 if it's orthogonal. The other way you can kind of think about it is that 0 vector is just like a dot at the origin. It's just not doing anything. It's not really perpendicular. It's not really parallel. It's just a little dot.
Gotcha.
All right. So we said that our cross product is given by this vector here. I'll just put an x5 for cross product. Our vector u is 1, -2, 1. How do we show if two vectors are orthogonal?
If the product is equal to 0.
Yeah, dot product equals 0. Okay, so going back to dot product, the easiest way to assess if two things are perpendicular to each other. So let's see if these guys are perpendicular. We're gonna have 3 times 1 is 3, 5 times -2 is -10, 1 times 7 is 7. Does that equal 0?
Yeah.
Yeah, so we're good. And we can check the same thing with 2. If we were gonna go through and check this with vector v, so right, vector v over here, 3, 1, -2. If we're going to find the cross product between the dot product between the 3, 5, 7 vector and this guy, 3 times 3 is 9, 3 times 5 is 5, 7 times -2 is -14. Does that also equal 0? Yeah, so we can see that they are indeed both perpendicular. If you went through and checked it with the other one in the other direction, it's still going to be perpendicular. Okay, one of them is just shooting off the positive direction, one's just going the other direction, but it's still perpendicular. It's like if we have that plane, right? One of the vectors can be shooting up in this direction perpendicular, one can be going down this way, but they're still perpendicular to it. So they're both perpendicular. We've got multiple answers here. These 2 ways to go through and find them. Okay. All right, so a bit more work in finding cross product, but getting an orthogonal vector turns out to be super handy. A lot of times we'll see this show up later on in other chapters here. We'll go ahead and pick up with this tomorrow to kind of review what we were working on and finishing up this section. So probably tomorrow is Thursday. We'll have a quiz beginning of the hour. We'll go through these notes here, and then I'll have another example sheet just with extra practice. Again, it still won't be for points, but just more practice problems to kind of work on. And we'll start 11:05 on Friday. Okay? So, as usual, try the homework. So if you have questions, we can go ahead and talk about them while this stuff is fresh in your mind. But aside from that, I guess I can give you a little bit of guide to what to focus on for the quiz. Quizzes are no notes, so it is you having to know what to go through and do. It'll be over finding dot products and cross products. Okay, I won't put that projection stuff on there because that's just a little blurrier to worry about. I want you to be able to find dot products and cross products, so we'll just focus on those. Okay? All right.
Could you go back one slide?
One more time, Edwin, I didn't hear you say a little louder.
Could you go back to the previous slide?
I sure can.
Yeah.
Okay. All right.
Thank you.
No problem.
What were you bringing again?
I was in Pooh Bear's group.
Oh, sorry.
Yeah, Pooh Bear. Yeah. I thought you meant like, yeah, I'm in your group.
That's right.
I was in Pooh Bear's group, and he's like, we're not coming down to you guys 5 more. And I was up there trying to go. I was.
Many, I mean, stuff like that, like the later round, I mean, early round is unexcusable.
Yeah.
The later rounds, he knows your stuff.
Yeah.
So as long as you
I
get-
wasn't, and I really wasn't slipping until that 3rd round.
that last round,
That last round was brutal.
yeah, I was watching this like you guys.